In this video, I'll show you how to use references, the range for loops, and the auto and const keywords. These are very much necessary things to know when you are reading or writing modern C++. You will learn to avoid some mistakes that would either cause outright bugs or to produce terrible performance. I have already written a function to print the contents of a vector here to make it easier for us to test what we're doing later. So I'll first show you that it works like so, and then we'll look at the function itself. It has a void return value, meaning it doesn't return any kind of value, and it takes a single vector int as an argument to print. And we'll improve this implementation here a little bit. So I have printed the contents in a normal for loop using the indices of the vector to print each item in turn. But notice that I don't actually care about what the particular index is I'm processing, and I want to go through all of the indices. In these circumstances, I can use something nicer than the old for loop. So I will comment this out, and I will write a range for loop to do the same thing. Here we go, and that's our range for loop completed. And as you can see, it produces the same result. So the structure of the range for is that instead of 2 semicolons inside here, we only have 1 colon. On the right side we have a container. All vectors are containers, all fixed size old C arrays are containers. Basically most data structures you have in C++ are containers, and all of the items inside the container are processed, each one in one iteration of the loop. On the left you have the data type of the individual piece of data in the container, and then a temporary name that you want this item to have inside the loop. And it's a lot simpler. We are no longer handling indices. We can't make many of the mistakes we might have made before. So we are not accessing the vector by index inside the loop anymore. We are just using the item that we got. And we can immediately improve this just a little bit further. Since the C++ compiler knows and we know that this vector contains integers, we actually shouldn't need to write a type name here. We shouldn't have to write int in this place, and we can instead write auto. And this essentially means, hey, C++ compiler, you already know what this type is, so take care of it. I'm not going to do it for you. And in here it's more of a matter of taste whether you use auto or you use int. But what using auto here does is it prevents accidental type conversions. Suppose this vector was a vector of floats. We are allowed to assign a float into an integer, but doing that cuts some of the information away, so all of the non-integer part would be lost. And if we then accidentally wrote int here, even though the vector contained floats, then we would accidentally cut out all that information. But if we write auto, then if the vector originally contains ints, we get I is int. If it contained floats, we get I is float, and so on. And there are other situations where we want to use auto. C++ typically has some very long type names, and they can sometimes get in the way of understanding the actual logic of the code and what the code is supposed to do. For example, if we had an array of arrays containing ints, like so. So vector int means an array of arrays containing ints. And then we would somehow assign data into it, and then we wanted to make a copy of this. Before we would have had to create a new variable with the whole type name and then assign. And this is, by C++ standards, this is still not a really long type name. There are much longer names than this. And you can already see how the unnecessary type name is starting to obscure the meaning of the code. So we would much rather just write auto, because the C++ compiler knows the type of the thing on the right side of the assignment. So naturally, on the left side, we want the same type. So we get this instead of this. So that is how we use auto. There's essentially no downside to using it. If in any circumstance the compiler doesn't know what the type is supposed to be, it will give you an error immediately. So there's no way to write bugs with this. It's a bit of a matter of taste how much you use auto. I personally like to use it a lot, and some like to use it mostly when it saves a lot of text, a lot of typing, but that's up to you. So now we have our print function. And the next problem we'll tackle is we want a function to change the contents of a vector. So let's try to do that. Again, I'll have a void. And I'll just try to assign into the first index of the vector. Just some value like so. And then I'll test if I manage to do that and print the results. Now, if we were in Java or C# or in Python, this would work. But in C++, it doesn't. So absolutely nothing happened. We were trying to assign 100 into the first index instead of 1, but the vector did not change. So why is this? All of the arguments of functions like this vector int here are copied. So v inside here is a copy of the v we had in main. So we modify the copy, and when the function ends, nothing has happened to the original. So everything in C++ is treated the exact same. Ints, all kinds of classes like vector, everything is just copied by default. And it's the same thing as what happens in simple assignment we've seen before. If we want to make a copy of a vector, we just create another vector variable and assign into that. It doesn't just move some kind of reference or create a new name. But that's what we have to learn to do right now. So to fix this, we'll use a reference. And a reference is part of the type name. It comes after the normal type here. and it means instead of making a copy, this v inside the function will be the exact same v that was passed in. So when we run, now we can see the vector is actually changing. So this prevents the copy from happening and allows us to modify the original. And you can see here we didn't actually change anything here at the call site. The only thing we changed was the definition of the function. So in the definition or the declaration of the function, we would see that this is a reference argument, but here when we are calling the function we have to actually pay attention, and the IDE will help us with tooltips and so on. We can point to this and see that it takes a reference. So because it takes a reference, it's likely that it will somehow change what we pass in. So what about the print function we had before? Now that we know every single argument being passed in here is a copy, unless it's specifically marked as a reference, now we know that this is also a copy. And that of course means that even if this kind of works, we are managing to print the contents of the vector, we are also causing a performance loss. In some other context, this vector might be even a megabyte in size if it's a vector that contains the data of a 3D model or something, and we could absolutely crash the performance of our program if we do this. So it's easy to fix. We just make this also a reference, which doesn't change the results we see, but it would drastically change the performance if we were calling this function a lot of times and giving it arguments that are large in size. And a small downside to this is that now by giving a reference we are also allowing this function to change the contents of the item we are calling it with. So if this function somehow accidentally changed the contents, we would not get any kind of warning. It would just happen. This is of course an artificial example, but it's quite easy to accidentally change something in a more realistic function. So we can also prevent that by using another keyword, const. And we can tag it on the type here, like so. Again, notice that nothing is changing here at the call site. We have just added const into the definition. Sorry, this, yep, so here, this was the actual call for the print function, and we'll see that the code is still working exactly as before, but the difference is now that we have a const vector here, we will get a proper warning when we try to do something to it. We don't even have to compile before getting the red squigglies here from the compiler, and we get the error message, expression must be a modifiable L value, and consts are not modifiable. So this is a lot cleaner and safer right now. There are other uses of const. There can also be some intermediate result inside a function that you want to mark as const, like so. And then you'll just assign to it once, and after that you are never allowed to assign to it again. but that's a bit more marginal. But it's important that you know how to use const in arguments to functions. And if you have a piece of data that is already marked const, you are not allowed to pass it into a function that requires a non-const argument, again because that function might have to change the argument, but const arguments are not allowed to be changed. And let's look at how to use references outside function arguments. Those can be quite convenient. So we can clean up code locally, avoid some mistakes, avoid some repetition by creating shortcuts. So essentially shorter names for something else. Suppose we had an array of arrays of floats, like so. And we would assign something in there. And then we wanted to test something very specifically inside there. Let's say we want to test if the third vector in here has a number larger than 1 inside its first index. And then if that's the case, we want to do something like so. So now what I'm doing here is I'm clamping that one specific value inside the array of arrays into 1 if it was something larger. And this is still quite a short name for C++. So we could instead give this particular float a temporary name, because this is just one floating point number. So we could say that we have a float reference f to this. So now after this line, f is exactly equivalent to some long name 3.0. And then we can write the code we originally wanted to write. And it's a lot neater. So this gives us some options to write our code in cleaner ways. And the last thing we're going to look at is returning values from functions. And this is a bit complex, but the conclusions are simple. So let's say we want to have a function that returns a vector of a certain size filled with a certain number. I'll call it make vector filled with some argument I. So I'll start off by making a vector. Let's say this always returns 10 length vectors. And I'll fill it with I. and this is actually not going to work, because the same thing as happens in function arguments also happens in the range for loop. So if we take just auto x or int x, that will be a copy of the individual element inside the vector result. So if we want to actually handle the elements, change the elements inside the range for loop, we have to use a reference. So auto reference x, like so. So now we are filling the whole vector, and then we return our vector. There we go. And then we'll test our function here. And I'll fill it with h and confirm that it works by printing the result. But nope, we get some trouble. And it actually comes from this previous code that we wrote, where we just assumed we would fill this array of arrays with something, but we don't want that now because it will just produce errors. So I will comment this lot out. And now we'll just examine our function that returns a vector. Here we go, it works fine. So we can see it works, but about these return values. Traditionally in C++, every return value from a function is also copied. So in some circumstances, when you return by value, you might get one more copy, and if your data is huge, then you could again have problems. But there has been something called return value optimization, RVO, that C++ compilers have been able to apply in situations like this, where you have a temporary variable inside a function which will cease to exist when this function ends, but you are returning it. So the compiler has been allowed to optimize by never actually destroying that value, but instead simply returning the value we have here inside the function. Until modern C++ and C++11, there has been no way to absolutely be sure that the compiler will do it. But starting with C++11, we can be sure. Every data type that has a so-called move constructor will always get return value optimized, and your own random class will not have a move constructor unless you create one, but every standard data structure, every vector, and so on in C++ does have a move constructor. So you are guaranteed that if the value you're returning is from a temporary variable here inside the function, then this return will basically cost nothing. So just something to keep in mind. And one more thing to notice about the range for loop. We already covered how you might want to use auto here to avoid accidental type conversion. Then there was how by default you get copies of the elements inside the container. If you want to change the actual elements, you need to use reference here again. And if you want to be super safe, and you know your range for loop is not supposed to change anything inside the vector, like here. Obviously printing is not supposed to change anything. You could even choose to put the const keyword in here, but that's mostly overkill. But it's really good to put const in function arguments when you don't intend to change that argument. So these are really important points to know, especially if you have no experience with the C programming language or earlier knowledge of the C++ programming language. The range for loops and auto in particular may not look like a big thing, but they totally change how writing C++ feels. So they are a huge change to those who come from old C++ knowledge as well. That's it for now.